Assalamu alaikum. Welcome to lecture number 29 of Digital Signal Processing. In this lecture, we are going to learn more about pole zero constellation with different configuration and how we can calculate the stability and frequency response of the system with the help of its pole zero constellation. After that, we will discuss the relationship between Laplace transform and Z transform, as one deals with the analog system and the second one deals with the digital system. So what is actually the relationship between these two transforms? After that, we will discuss the stability region in Z plane, which is the graphical representation of Z transform, as we are more interested in Z transform as it deals with the discrete time signals. Here we will learn more about different pole zero configuration. Again, we have S-plane. X-axis is marked as sigma and y-axis is termed as j omega, and here we have these two poles in the previous example, but now I am going to discuss the comparison between the frequency response if I shift these poles towards the y-axis, which means that if I shift this pole to this new position, which is much closer to y-axis, what effect we will observe in the frequency response? Whatever the effect for shifting valid for poles, the same effect is valid for zeros. We are just trying to find out what if I shift the roots of this system towards the y-axis, or vice versa, away from the y-axis. For example, if this pole is shifted away from the y-axis, same is the case with this pole can be shifted away from the y-axis. Yes, this can happen also. So what will actually happen to the frequency response? Generally, we can say that if we move roots towards the y-axis, then the response will become sharper. Whatever the root is, whether zero or pole, our frequency response will become sharper. For example, if you have two zeros instead of these two poles and these two zeros are shifted to this new position, then we have the same sharper response for zeros also. The response is not the same, but effect is the same, that is the sharper response. So first, considering regarding the poles. For example, if we have poles at this previous position, we have frequency response like this. I have plotted with fainted line. This is the response which we were obtaining previously, but as you can see that these two poles are shifted towards the y-axis, so our response will become sharper, and this is the response we will obtain from this new position of poles. You can see that this response is not sharper, but as we moved the pole towards the y-axis, response become sharper. If we move further this pole towards the y-axis, then this response will become more sharper. And what happen if the pole exactly lie on the y-axis? Then we will get exactly infinite value at this point. So same can be plotted for Fourier transform. We have this normalized frequency response. This response, which is shown by a fainted line, is the response we were obtaining previously, but as the poles are shifted to this new position, then response is become sharper. So if there is a zero lie there, then the response actually attenuates and the attenuation becomes sharper. Here you can see the gain is becoming sharper. Previous gain is this and present gain is this, which is sharper gain. But if a zero was there and zero is moved to this new position, then actually the attenuation becomes sharper. So this is actually the effect of moving pole and zero away from the y-axis. Now for our better understanding, I have included roots which have some zeros in it in addition to the poles. You can see that these two are the poles and we have one zero in this system also. So we are going to analyze the stability of the system as well as its frequency response from this given pole zero constellation. First of all, regarding the stability, we have to see whether all the poles lie in the left hand side of the S-plane. Yes, all the poles lie in the left hand side of the S-plane. There are two poles in the system which are on the left hand side of the S-plane, and as I already stated that this zero or any zero will not contribute to the stability of the system, so we will not see the position of zero. Zero can be on the positive x-axis or maybe on the negative x-axis. It will not affect the stability of the system. But if any of the pole lie on the positive x-axis or the right hand side of this plane, then it will create a problem and it will make this system unstable. But as far as this configuration is concerned, we may comment that this system is stable as both the poles lie on the left hand side of the S-plane. Now what about the frequency response? Again, we have to move along the y-axis. When we encounter pole, we will provide gain to the frequency response, and here we encounter zero also. So we will attenuate the frequency response when we encounter a zero along the walking track, and again we have a pole, so our response will again rise at this zero and then reduce to the normalized value. So actually we will have the response like this. You can see that we have a normalized response because we are approaching pole, so our response is rising and it has a peak value exactly at the pole frequency, and after crossing the pole frequency the response is reduced to the normalized value. But as soon as it reduces to the normalized value, it encounters a zero along its walking track. So the response is shifted or attenuates below the normalized line or normalized response because of this zero. So when this exactly zero is encountered, the gain attenuates to its maximum value. As I draw this frequency response with the help of pen tool, so this is not a very sharp response, but you can understand it by understanding the idea of providing attenuation and amplification in the gain. So here with the help of pole zero constellation and S-plane, we actually determine the stability of the system as well as the frequency response of the system. This same response can be obtained with the help of Fourier transform. You can see we will get the same frequency response, but in this response we cannot comment regarding the stability of the system as Fourier transform is not concerned about the stability of any system. Now for our better understanding, we will consider a case where the poles of system lie in the right hand side of the S-plane. As you can see, we have sigma along the x-axis, j omega along the y-axis. Both are forming S-plane, and very interesting to note that poles of this system lie along the right hand side of the S-plane. So we can easily comment that this system is unstable system. However, we can also calculate the frequency response of this system. How? We have to move along the y-axis, and here we encounter a pole, so our frequency response will amplify and again normalize, and the second pole is encountered, so our frequency response will again amplify and reduce to the normalized value. So in general, I have plot it with the help of pen tool, and this rough sketch is obtained, which is showing that I have amplification in the frequency response when I encounter the pole frequency. So although this system has some frequency response, but by looking at the S-plane representation, I can conclude that this system is an unstable system. But this statement cannot be given with the help of Fourier transform. If you look at the Fourier transform, which only deals regarding the frequency and its magnitude along the y-axis, so it only plots the frequency response. By looking at this response, no one can predict that this system is an stable system. So this is basically the drawback of Fourier transform. That's why we don't use Fourier transform to analyze any system. We only use Fourier transform to analyze signals. For system analysis, that's why Laplace transform is preferred, because along with the frequency response, it also tells us regarding the stability of the system, which is verified from this pole zero constellation, that although we are obtaining some frequency response, but this system is not an stable system, as the poles of the system lies on the right hand side of the S-plane. We can have many other different possible combinations of poles and zeros of the system on this S-plane, and we cannot discuss all of them obviously, but I give you the concept of plotting the frequency response with the help of given pole zero constellation, as well as how to determine the stability of the system with the help of given pole zero constellation. So for your practice, you can sketch more and more poles and zeros on the S-plane and try to determine the stability and frequency response of that system for your practice. And if you need any of my support, you are free to ask through email or using the facility of live session. As I already stated that Laplace transform is used to analyze systems which are analog in nature. But as far as digital signal processing is concerned, we are dealing with the discrete time systems. So to analyze discrete time systems or digital systems, Laplace transform basically fails there. So if we need to analyze any digital system or discrete time system, we need some robust tool, which is the Z transform. Z transform is basically the transformed version of Laplace transform, which deals with the discrete time system. So as we are more familiar with the Laplace transform as well as its stability region as well as its pole zero constellation, so we will try to transform all those concepts on the Z transform. By this way, we will learn how we can determine the stability and frequency response of any discrete time system. So first we have to analyze what is the relationship between Laplace transform and Z transform. As you already know that Laplace transform deals with the continuous time system, as you see it with the integral sign as well as the limit, which is minus infinity to positive infinity, and the signal is denoted by x of t. So this is basically the expression of Laplace transform. This one is the mathematical expression to calculate the Z transform of any discrete time signal. This expression is basically used to transform any discrete time signal into Z domain. Here we are interested to determine the relationship between Laplace transform and Z transform. So in the first equation, which is of Laplace transform, you can see we have S variable, which is denoting the complex frequency. Why we are calling it complex? Because it is comprises of sigma and j omega. Sigma is basically the termed as Napier frequency and omega is termed as radian frequency. So both of these frequencies combines together to form the complex frequency. So S is basically complex frequency represented in Cartesian coordinate system. And what about Z transform? In Z transform, the same frequency, which is complex frequency, which is earlier represented in Cartesian coordinate system, is just transformed to polar coordinate system to fit in this expression. So basically the transformation is very simple. Laplace transform represent the complex frequency in Cartesian coordinate system, whereas Z transform represent the complex frequency in polar coordinate system. As you all know that in Cartesian coordinate system we have x-axis and y-axis and both are orthogonal to each other, but in polar coordinate we mark some point with the help of radius and angle. We will try to explore this further, as z is equal to e raised to power s by comparing the first and second equation, as t variable is eliminated because here it is continuous time domain and here we are dealing with the discrete time domain. So t is replaced by n and integral is replaced by summation sign because we have discrete sample values. So z is equal to e raised to power s, and if we try to further expand this s by sigma plus j omega, then z will become e raised to power sigma into e raised to power j omega. So these two basically are making the z, which is the magnitude, and the angle, which is the basic representation of polar coordinate system. So we can write z is equal to r angle omega, and by comparing these two equations we came to know that r is equal to e raised to power omega and angle is basically the same angle represented in this Cartesian coordinate system. So in this way we can just transform the complex frequency from Cartesian coordinate system, which is sigma plus j omega, into polar form, which is r angle omega, and r can be calculated by using this relationship. R is equal to e raised to power sigma, and angle can be calculated by simply taking the angle of this basis function. So this is basically the relationship between Laplace transform and Z transform. Now we are going to discuss the relationship between its pole zero constellation or its graphical representation. Now we are going to find out the stability region in Z plane. As we already know that the stability region in S plane lie on the left hand side of the plane. But what about Z transform? How we can actually determine the stability by looking at the pole zero constellation? It is very simple. we just try to utilize the information of stability region in S-plane, and as the Laplace transform and Z transform are basically the version to determine the system in analog domain and digital domain respectively, so the same concept is transformed to the Z plane. Here you can see this is the expression of Laplace transform, and now the expression is expanded for as complex frequency is equal to sigma plus j omega, and we know that the stability region of S plane is for sigma less than or equal to 0, or we can say that sigma can vary from minus infinity to 0. So this particular information can be utilized to actually determine the stability region in Z plane. If I plot the S plane, then sigma is along the x-axis and j omega is along the y-axis. So for this S plane, we already know that the region on the left hand side is stable region. But what about the Z plane, as it is basically the polar representation of complex frequency? So the radius is equal to r is equal to e raised to power sigma as calculated in the previous slide. So we have two limits of sigma here, minus infinity, and the extreme limit is 0. We cannot move beyond 0 because after this value the system will become unstable. So we have to remain in this range to make the system behave stably. So for this range, the first extreme is minus infinity, so I put sigma is equal to minus infinity, and the other extreme is sigma is equal to 0, so I put sigma is equal to 0. So in this way I will get to know the range of the stability region in Z plane. When I put e raised to power minus infinity, my radius turns to 0. It means from the radius starting from 0 value to the radius ended up at 1 unit, which means a circle which has a radius of 1 unit is the stable region. As much as poles lie under this region, which is radius of the circle starting from 0 to 1, which is a unit circle, is basically the region of Z plane in which this system is a stable system. After the radius of 1 unit, system will become unstable. So the range of the stability region in Z plane is a circle of unit radius. If I want to express the S plane and Z plane graphically, then for S plane you already know sigma and j omega are orthogonal to each other, and this constitute a S plane which belongs to the Laplace transform. And for Z plane we came to know that basically we have a complex frequency represented in the polar form. So in the polar form, x-axis is basically the representing the real value and y-axis is basically representing the imaginary part. And as far as the circle is concerned, so you already know that the angle of circle can vary from 0 to 360 degree for a unique cycle. So here 0, pi by 2, minus or plus pi, and again minus pi by 2 or 3 pi by 2. So in this way I can draw a circle of unit radius, which is basically the representation of z plane. Here you can see the graphical representation on the right hand side is for z plane and on the left hand side is for s plane. This basically is representing the analog system and this is basically representing the discrete time system. And we also know that the range of frequency which are unique in discrete time system can vary from minus pi to plus pi, because after that point the circle going to repeat itself. And regarding the pole zero configuration, all the poles lie inside this circle will make the system stable. But if any of the circle lie outside this circular region will make this system unstable. And what about at this circular boundary? The pole at this boundary will make the system marginally stable, because if I shift the pole from this line to this area, the system will become stable, and if I move away from this line, then the system will become unstable. So this solid line is basically the unit circle of radius 1, and all the poles lie within this region will make the system stable. So this region is basically the stable region in Z transform. Now we are going to learn how we can transform the pole zero constellation if given in S plane to the Z plane. For example, if I have some analog system which have some particular response and I want to design it digitally due to its advantages, how I can transform the system information in terms of pole zero constellation in S plane to the pole zero constellation in Z plane, because after this information I can easily design the system. So here is a question. Find out the equivalent Z domain locations for the given pole zero constellation in S domain. Here I have S plane in which sigma and j omega are orthogonal to each other and pole is marked at the center. This I have just taken for example. You can try with a different configuration of poles and zero when you will learn this concept, that how one can transform from S domain to Z domain. Now here we are provided with a single pole lie exactly at the origin. Now we have to determine its equivalent Z domain location, that where this pole actually lie in the Z plane. So we know that for this particular position, which is the origin, sigma is equal to 0 as well as omega is equal to 0. So by utilizing this information, I can actually calculate the radius of the circle as well as its angle. Angle is very simple and straightforward. As omega is 0, so the omega is same in the Z plane as it is in S plane. So omega is same 0 in the Z plane also. I have just to determine the value of the radius of the circle at which this pole will marked. For this, sigma is equal to 0 is considered, and I put the value in the formula. R is equal to e raised to power sigma, and sigma is equal to 0 as given in this S plane. So radius is found to be 1. So if I plot this in the S plane, then I have all the information for plotting. Radius is 1 and angle is 0. So now I am going to plot this in Z plane. In Z plane, you know that I have two axes and angles are marked accordingly: 0 plus pi by 2 plus minus pi and minus pi by 2. Again, a unit circle is drawn and the pole is exactly laid on the radius of the circle, which is the position indicated by my pointer. Here you can see the boundary of the circle is representing radius 1, which is this, and angle is 0. So pole is exactly along the x-axis at this position where my pointer is. If, for example, omega has some different value, for example, omega is shifted to this position, which is found to be plus pi by 2, then I will mark the pole to this position. Or if some other value of omega, the same value of angle is marked on this unit circle, and then the pole is plotted on that position. But for this pole position, I know that omega is 0 and radius is 1, so the pole is marked to this pointer, this position where the pointer is placed now. So in this way you can easily practice with different pole 0 constellation. Just try to find out its radius and angle, and accordingly you can transform the S domain pole 0 constellation into Z domain pole 0 constellation. And it is very interesting to note that once I provided with the pole 0 constellation in Z plane, I can easily determine the frequency response, or vice versa. If frequency response is given to me, I can plot it in the Z plane, and from the Z plane pole 0 constellation I can actually drive the mathematical expression in terms of transfer function. And once transfer function is obtained, I can easily design my infinite impulse response system. So that's why I said there, to design infinite impulse response system we need to learn Z transform, because with the help of Z transform we ended up with the pole 0 constellation. Because if you want to design any system, you must begin with some frequency response, and for that particular frequency response there must be some pole 0 constellation in the Z plane, and with the help of this pole 0 constellation we can actually drive the transfer function. And once transfer function is obtained, as it is the mathematical expression, we can easily design an infinite impulse response system.